Hello everybody. Welcome to Chapter 15 of your statistics course. In this chapter we're going to talk about inference with regard to regression models. For this, we would like to consider testing individual independent variables and their betas, as well as looking at the entire set and collective of all independent variables in a joint significance test. In addition, we'd like to see if we can test some restrictions, that is, let it run as a complete unrestricted model, then consider restricting or simply taking away independent variables and see if they're actually necessary. We'll look at other forms as we move forward in statistics to see if we can eliminate variables one by one, but in this case we'll do a complete linear restriction. Now to start, let's take a look at a simple case. Let's analyze the winning percentage in baseball. Here's a bunch of baseball teams, and what I've done is also put out for us a spreadsheet. And this spreadsheet will be available to you on our Canvas site. And with this spreadsheet, we're looking at winning percentage versus batting average and ERA for all the teams. And a lot of times people quarrel over what these individual statistics like batting average and ERA for a team do to winning percentage. So what we want to know is does a team who has a higher batting average, does it have a better predictor of winning, or is it a low earned run average, or maybe both? Maybe together they have an impact. So what we're going to do is we're going to compare batting average versus winning percentage, ERA versus winning percentage, and then both batting average and ERA taken together versus winning percentage. And it'll look something like this. Considering that these are models, so they have beta in them, we haven't estimated it, they haven't converted to B's yet. Also notice that they have error in every single one. So we have one independent variable, and then two. What we'd like to be able to do is run them as models. So what I'm going to do is this. Let's take a look at this individual data. And what I've done first is run a simple model. Remember, what I'd like to do is from data analysis, with respect to regression, and what I'm going to do is highlight the win, that's my Y as you see noted, versus X. So let's just do batting average. So in this case it's a column C, and I'm including the titles or labels. So what I'll do is I'll click labels, and I'm going to click output, and I'll put it right here in cell G2. You can click on residuals, and that will give you all the error terms if you'd like. But in this case, we will just put it here. Now, I've already run it and highlighted. By doing this, you'll get the same solution we have. Get rid of this. And I would do the same thing for just running the ERA. But if I wanted to run both, I would do data analysis, regression. It's going to keep stored C. Now I'm just going to highlight both D and E together. So D2 to E32, that will copy. And I'm going to move that guy over here somewhere, as you'll see. Move him right here. And I would just simply run that regression. Now I have three separate regression. One for just batting average, that's the first set in column G starting, column Q for the ERA, and column AA for both. You'll see that I've pulled the same information. So what we have for each one is their multiple R. That's simply their correlation. Something called R squared, that's the coefficient determination. It simply is squaring R. Remember, that tells us how much of the total variation in win percentage can be explained by the independent variable. In this case, 21.12% of the winning percentage can be explained by batting average. In this case, 44.65% of the win percentage can be explained by the variations that's happening in ERA. And in the third case, notice there's something called an adjusted R squared. Adjusted R squared adjusts, as we know, for the number of independent variables. So you notice we use R squared, but when we have more than one, we have to use adjust. It actually penalizes us for using more than one variable. So the adjusted R squared is the one we looked at for multiple. The win percentage versus both. So 69.45% of all the variation in win can be explained by these two, meaning only about 30% is left to chance. Obviously, they have standard errors, and they all have the same observation counts. So just looking at this in terms of what can be explained, Obviously, almost 70% can be explained by both of them together versus the other two, which is significantly less. So from a fit perspective, it looks like having two variables is the way to go. But that doesn't mean they're significant. What we like to do is take a look at the total number, and this is our normal model. Notice K represents the number of independent variables, 1 to K. And what we're going to do is test individual betas to see whether or not they're equal to, greater than, or less than. Now, almost all the time we look to see is a two-tailed test. Is beta equal to 0 or not? That is, can I set the leading coefficient to 0 and have that variable disappear and see no real impact on the overall regression? That is it significant in its impact? So we'll have a statistic, obviously a t, based on what you believe the beta to be, what the value as realized from the sample, and there's a standard error. Most importantly, realize that the t distribution we use, because it is drawing from a sample and creating sample values for the standard deviation, the k, remember, represents the total number of variables in the model. So the larger the sample size actually impacts the degrees of freedom. Most commonly, we set beta to 0. So what we would do is test this entire model and then test each and every beta versus x combination to see if we can set beta to 0 and not really change very much. If we can set it to 0, it just simply says it's not a significant predictor or not significant in the prediction of this. Now, more often than not, we're going to use Excel. We're going to be able to use the p-values and statistics generate from it, including a confidence interval, and I'll show you how to do that in a second. But we're going to test this over and over and over again. So let's take a look. So for the very first model, for BA, as we know from regression, the first thing that we're going to do is look at significance. Now this is an ANOVA, and we'll revisit this in a little bit. But there was one independent variable. There were a total of 30 observations, so 30 minus 1 is 29, and therefore you have to balance to get 28. So 1 plus 28 is 29. The sums of squares is additive down, so this plus this is this, and then you'll divide each of the sums of squares by their degrees of freedom and get the mean squares. These are measures of variation. Their ratio creates an F, as we saw in Chapter 14, and now we have this thing called significance. This is a p-value, and you compare this to an alpha, say 5%. Since this is less than, say, 5%, let's just do that, 0.05, 0.05, the regression is significant. So we have a significant regression here because the model itself is significant. But notice by itself, the p-value associated with batting average is the same. So this versus this is exactly the same. So I'd like to see if I can draw some kind of an association. What I'd like to do is create something, and let's just do this. Let's grab something like this and show you that this and this are exactly the same. And that's because this says all the variables taken simultaneously in the model, well, there's only one. So the p-values are going to be the same. So in this case, batting average is significant. The intercept also has a p-value, but the intercept is really nothing more than a balancing item. So it being significant, it has no importance. It's trivial. Just to be clear, this p-value I get right here can be generated. I simply take a look at the t statistic available to me, and I take 30 sample size minus number of variables, there's only one, minus 1, and I get that value. I would do the same thing if I were to run ERA. In this case, since its scientific notation is negative, that means it's 0. So this 2 would be significant. This 2 has a value that's the same here and here. Let's show a quick additive. These two are the same. So obviously ERA is significant. Now I come to the last one. As I look at the significance of the model, we'll get to that in a second, totality here, but both of the p-values associated with ERA and batting average have p-values that are 0. Again, I could calculate them based off their t-statistics, but their p-values are significant. They're both less than 5%, so batting average and ERA individually are significant. And that's what it's saying here. For the totality, the p-values are 0, therefore we reject the null and say that we can't set the beta to 0. In either case, they're significant. Both are significant in their prediction. We can also see them as confidence intervals. And I'll just show you a quick one over here that I can create a confidence interval using the coefficient plus or minus the normal t-statistic times the standard error. And all I'm going to do is say 95% is take 3.005 minus the t-statistic times the standard error, and I get 0.757, and the upper is just add that. And notice in this boundary here, there is no 0. If 0 were in there, that means that we could set batting average to 0 and get away with it and say we would not reject the null. In this case, 0 is not in here. If I come over here, you'll also see that we have confidence intervals, and neither one contains 0. One's negative, one's positive. So we're able to create those things. I got ahead of myself a little bit ago, but let's just take a look now. Joint significance. What I'm saying in joint significance is the entire set. If I take all the betas simultaneously, can I set them all to 0 and walk away and find out that none of them have an impact? Or if I reject the null, at least one of them does. So when I showed you this before with the significance, setting up through the ANOVAs, there was only one variable. So there wasn't really a test for joint significance. It was a single significant variable. Here I have 2. So what I'm going to do is say that there were 2 variables. So in the regression, there were 2 variables. Degrees of freedom was 2. There were 30 minus 1 in total. We always reduce by 1 in this case. So 2 minus from 29 is 27. Sums of squares are generated. The mean square is nothing more than the sums of squares divided by their degrees of freedom. Copy that down. The F statistic is the mean squared of the regression by the white noise or residual. It's what the regression can explain in terms of variability versus what it can, and that's white noise. And then you'd have a p-value or significance of F. This is the p-value for the joint significant. If this value is less than 0.05, as we saw before, we would say that the regression is significant. So at least one of the variables is going to be significant. So the first thing you would do is run a regression. First thing you would check is to see whether or not it's a significant regression. If it is, check its adjusted R-squared. In this case, about 70% of all the variation in wins can be explained. Then you look at individual variables and find out which ones are and which ones are not significant. And I've just described this, and I showed you how to do all this within the Excel, but we're looking at an F ratio where you take the mean squared of regression, that's the variance of regression, over the variance of just the white noise or error. That F statistic, as we saw when we did things, we looked at variability in Chapter 11, we're able to look at the numerator, which is the mean square. We want that value to be significant because the more variability that can be explained by the regression, the less is left to chance. And in the end, the p-value leads the way. And what we find is that the p-value was significant. That's what's happening here as we create this. And if you want to look how we do this, it's just an f.dist statement in Excel. We know that we've had the ability to look at the different fit measures. We already talked about at the beginning, but comparing the R-squared of the univariate on the independent side versus having 2, Model 3, which has both the ERA and the batting average in it, seems to be the one that has the best fit. It has significant regression and individually it's significant variables. So they're both great, but together they're even better. The last thing we want to talk about is a test of linear restrictions. Say, for example, we have 3 independent variables, and we're trying to use them to explain things. what we'd like to know is, can I set two of them to 0 and see if doing so does just having the 1 show any difference from having all 3? And if you can do that, you can eliminate 2 and 3 and say, you know what, I don't need them. What we're doing is a partial test. Excuse me. What we'd like to do is look at a restricted model where we don't estimate particular variables and their coefficients versus an unrestricted model, which is an everybody in model. And what we're going to do is compare the sums of squares of their white noise or just random error of the restricted and the unrestricted. And with this, as you can read, the restricted model's error sum of squares will not be significantly larger than the unrestricted if the restrictions are valid. That means we can get rid of them. So what we'll do is take a look at the SSC of the restricted minus the SSE of the unrestricted. It has a measure of degrees of freedom, where the numerator of degrees of freedom is the number of restrictions. So if you have 3 and you're restricting 2, that number's 2. The denominator is the same thing, where we're taking a look at the total number minus the number of variables you're looking at in total, 3 minus 1. And what we're trying to do is look at the critical, in our case, the p-value, because in business statistics we look at p-values more often than not to see if we can reject a null. When we reject the null, that means that, well, if we go back, we can look at the hypothesis just to give us a chance. Can we set these things off? Well, let's go see if that's true. So what we're going to do is look at a car wash company in Missouri and see if promotions improve sale. We're going to look at the sales across 40 counties, see if a discount rate applied, the radio advertising in thousands of dollars, and newspaper sales, newspaper advertisements in thousands of dollars. Sample size of 40. Sales as their independent variable. Can we set them to 0 or not? We're going to see if discount by itself can predict sales, or from the unrestricted, take all 3 and throw them in. And let's take a look at how we do that. For car wash, here's the price, radio, newspaper, and if I run just price, that's with the restriction of radio and newspaper out. We've seen that regression. I showed you how to run that. We find out we have, quickly, a significant regression. So the p-value is significant, so it's significant. And its r-squared is 35%. If I run all 3 of them in together, remember, running all 3 requires me to do regression analysis, where I come over here and I choose 1 for the y and all 3, all their variables and their data, across all 3. And I'll do that for both. Try that again. Here's sales. So I have all of A, all of B through D. I'm just going to put it out here somewhere. And if I do that and I run the regression, I'll get this. Again, is it significant just to follow all the rules? Is it significant? Yes. What about the p-values? Well, we have p-values that are significant. Yes. Doesn't really matter. The total adjusted r-squared looks pretty good. It is explaining about 61%. And what I'm going to do for the f statistic is pretty simple. I'm going to take the value of the sum of squares error minus, for the restricted, minus the unrestricted, and divide that by a particular value. And you'll see what I'm doing here. The value is 2, because that's the number of restrictions. There's 38 versus 36, or just 2. That's the number of restricted. All compared to, in the ratio, go back again and get it, the unrestricted divided by its total degrees of freedom. That would be, I've got 40 minus 3 independent variables minus 1. That gets us to 36. And that gives me an f statistic, which I then convert to a p-value that tells me, notice I'm taking it from an f dist perspective, where I take the f, 2 and 36, And I will then say that because that is less than, say, 5%, I reject the null, and I will say that at least one of the coefficients, we go through this, we reject the null and conclude that the restrictions are not valid. At least one of them has to be included. One of them is going to be proving significant. Another quick one. What if we want to know if two of them are the same? Well, they're either the same or they're not. It's a different kind of restriction. So what we'll do is run the unrestricted 1, 2, 3 versus what if we can say set them equal so that their beta would be the same. So we set the beta 2, and we'll make the radio and newspaper additive. In this case, because they're in thousands of dollars, it makes sense. Sometimes it doesn't make so much sense. There are all kinds of convoluted models that could look at multiplication, different kinds of things. We'll look at simple additive. So what I've just simply done is say, here's radio and newspaper. We saw this before, but I'm going to make them additive. I'm going to run price discount. And what I would do is run it AB. And so I have the new AB column from column C and get its regression. It's significant. Its p-values are significant. The adjusted R squared is 60%. And over here, I'm going to see the same, something very similar. In this case, I'm going to run them all. I ran that before. And we'll go through the same process of creating an F statistic and its p-value. Now, in this case, the p-value is quite large. In this case, we don't reject the null. And if we go back here, we'll see by not rejecting the null, we're going to find that they're equivalent. So that's what we do in this chapter. We'll move on to chapter 16 next to continue our discussion of regression.